Okay, I'm just gonna send out the form. There you go. And we are here actually, or here. Okay, so we are on this problem where we are trying to make cost optimal. We want to know where to locate this point so that cost is minimum. All right, and basically this is the cost function. So I called this y, this whole thing is 8. Therefore, this is 8 minus y. This is x, which is the distance underwater. Here is the cost. 1 million times x plus 500,000 times this distance, which is 8 minus y. And again, this cost function has two variables. We want our function to be a function of one variable, so we look for a relation between x and y. And this triangle here gives us the relation, which is 5. This had to be given. So the square of this measure, 5 squared, plus the square of this measure, y squared, equal to the square of the distance underwater, which is x squared. And then you can solve this thing for either x or y to plug in here. Again, it doesn't matter what you solve for. I solved for, what did I solve for? I solved for x. Just take the square root and that gives you x. I know that when you get x, there is a plus or minus. We know that, but here we are looking at distance. So you can't have a negative distance. Therefore, you choose the positive. Plug your x into the objective function. This is what you get. Function is no longer linear. It involves a square root. Take the derivative. Variable here is y, so you're differentiating with respect to y. This is really dc dy. Using chain rule here, this is the derivative of the square root. And then here you have the derivative of negative y is negative 1 times 0.5. You get negative 0.5, set equal to 0. And solve for y. There's a bit of algebra. You move that negative 0.5 over, you get positive 0.5 or half. I left, yeah, so I kind of decided to leave that or rewrite that 0.5 as 1/2 because it's easier to deal with. We have a square root over here. Oh, by the way, I multiplied by the square root to get rid of the fraction. This is what we get, and then we want to get rid of that square root, so we square every factor. This is the equation, which is quadratic because we have a square, degree 2. To solve this equation, you can multiply by 4 to get rid of 4. Let me see if I could shrink this stuff a little bit so that there is enough room. Actually, I'll shrink the whole thing. Okay, so multiply by 4 to get rid of that 4. You got 4y squared equal to 25 plus y squared. Okay, this is quadratic, but it's not a bad quadratic function because you can isolate y squared and take square root. Just subtract y squared, you get on the left 3 y squared, on the right 25, divide by 3. Thankfully, 25 is a perfect square, but 3 is not. Okay, so when you solve for the critical value, you get y equal to positive or negative 5 over root 3. Of course, we just killed a negative because we are looking at distance. Y can't be negative. Okay, so just get rid of that. This is the critical value. It's the only critical value. And now you need to show, well, let's see what we are asked. Yeah, so they're asking where should P be located to get minimum cost. So we just want Y. Okay, you want the distance from A to P. That distance is simply Y, which is what, and we found it. We just have to show, that this gives us absolute max of the problem, of the objective function. Okay, we need to show that. There are two ways that you can do this. You can plug in the endpoints and the critical value to show that the critical value gives you the lowest, not the highest. I think I said the lowest cost, lowest. Okay. And remember that the extreme value theorem says that if you have a continuous function, our cost function here is continuous. If you have a continuous function, then the function attains its absolute minimum and maximum on a closed interval. So just plug in cost at 0. We want cost at that critical point and cost at the other endpoint. Okay. Yeah, so let's plug in cost into the cost function right here. You get square root of 25 plus 0 squared. Y is 0 here, plus 0.5 times 8 minus 0. Okay, so here what we get is 5 plus 0.5 times 8 is 4. That gives us, what is that? Is that right? Yeah, 5 plus 4, 9. Do I have that right? Yeah. Okay, so that's cost, and it's in millions, so it's 9 million. And then let's plug in 8 because it's easier. You got square root of 25 plus 8 squared plus 0.5 times, I'm plugging 8 for this y right here. So 8 minus 8. And that gives us, so 8 minus 8 is 0, second term is 0. And then we have here square root of 25 plus 64. And that gives you about 9.4. Okay, so what does this mean so far? This means that, guys, think about this. Don't just write answers down. Okay, in reality, if you're working for a company, you trust me, you are gonna naturally do this. Okay, because your butt is on the line. Don't just get values and say, oh, I'm done, I'm getting an A. So here, 9 million, cost of 9 million means that when y is 0, so y being 0 means that P is right at A, which means that you are going to run the pipe directly to A and then on ground to B. This is the path that you'll take to transport the pipe, transport oil. And if you do that, your cost is $9 million. That's what it means. Okay. C being a cost at 8 means that if y is 8, do I have that right? Yes. If y is 8, then P is right at B. So that means that you're directly transporting oil from the oil well to B. And if you do that, your cost is going to be $9.4 million. $9.4 million. So obviously that's more expensive because running the pipe underwater is expensive. Okay? So you might think that, hey, this is better, but yes, it's better among these two, but let's plug that in and see what we get. Okay, so plug 5 over square root 3 into, again, the objective function. You get 20 square root of 25 plus 5 over root 3 squared. Okay, plus 0.5 times 8 minus 5 over root 3. And for this one, I for sure need a calculator because I'm dealing with a rational number. Okay, so let me get this on the calculator for you. Yeah, this gives us approximately $8.33 million. Yeah, so obviously this is the smallest of 3. Okay, now you see why I am plugging in the endpoints as well as the critical value. This gives you a lot of good information. Okay, it does. You know your cost at those endpoints and at this critical point. Okay, so obviously this is smallest, and that's what we want. Okay, so you want to go with this option. All right, so this means that if I locate P, whatever, 5 over root 3 miles away from point A, then cost will be smallest at $8.33 million. Okay, and what's 5 over root 3 anyway? Let me see, 5 divided by square root 3 is about 2.9 miles. Yeah, so if P is located 5 over root 3, which is again about 2.9 miles from A, then cost is minimum at $8.33 million. Okay, is it kilometers or miles? Oh, it's kilometers. Okay. Yeah. This stuff is used in reality, okay? People use this stuff in everyday things. Well, okay, and of course, economics and a lot of other things. Can you imagine before calculus was really discovered, people had to really sit down and try things out and look at all the masonry and all the buildings that were put up. 600 years ago, 1,000 years ago. A lot of architecture and engineering went into it, and there was no calculus. People had to sit down and try this numerically. People had to actually sit down and choose a bunch of values, and they wouldn't get the exact solution. So if you were to do this before calculus was discovered, you would have to try different values of y. You had to pick like 100 different values for y to see which one gives you the smallest. You do this stuff numerically, but now we have calculus. Okay, so I think that was the this is the only minimization problem. I think this one is also a minimization problem here. Let's talk about this. This says that a closed cylindrical can, so right circular cylinder like that, is to hold 1 liter of liquid. How can we choose the height and radius of the can to minimize the amount of material needed to construct the cans? This is what I was talking about yesterday. Like these soda drink companies, they are required or they're mandated to fit, like, let's say 1 liter is a little too much for a can, I guess. But let's just hypothetically say they're required to fit 1 liter into a can. Okay, volume is given here. This is the constraint. Constraint is that you have to put 1 liter of, screen is frozen, liquid in the can. There are so many ways that you can accomplish such thing. You can make your can look ridiculous like that. Okay, this can hold 1 liter of liquid. Okay, if you make the height long enough, given a certain small radius, you can try to fit 1 liter, or you can just cut down from the height a little bit, make the radius bigger, and then you'll be able to hit also 1 liter. Or you could try to be like reasonable. You know how people do these? They go based on Fibonacci ratio, by the way. They don't go based on strictly calculus. They go based on Fibonacci. Because with a can of Coke, probably if you do calculus, you come up with something like that to fit 1 liter of Coke, but such can doesn't look natural. Can you imagine going to market and getting a can of Coke whose height is 3 times the diameter? That kind of looks ugly, right? It does look ugly. It looks unnatural. So the way that they choose the height and diameter of the can is based on the Fibonacci sequence. It's based on the golden ratio, which is about 1.6. If you take the ratio of height to diameter, that ratio has to be 1.6. That looks good, okay? So they go based off of that mainly. I know they want to be optimal, but I know it's a lot. It's a lot, right? But imagine a can of Coke. Okay, it's like half a liter or a quarter liter. But still, in my opinion, they go based on what looks good. A ratio of height to length to width, or height to diameter of 1.6 is good. Where does 1.6 come from? 1.6 comes from the golden sequence. The golden sequence, I don't know if you know it, it's 1, 1, 2, 3, 5, 8. Next one, 13, 8 plus 13, 21. Then you do 13 plus 21 and so on, 34. This is the golden ratio. And if you were to take the ratio of any two consecutive terms, if I were to take 21 divided by 13, I get around 1.6. You can try. If you take 13 divided by 8, try it out. You get something around 1.6. 8 divided by 5, around 1.6. 1.6 is the natural ratio that happens a lot in nature. And that's what they typically use. Yeah, so I mean, this is just hypothetical, okay? It's a can of lard. I don't know what the heck it is. 1 liter in a can, yeah. I guess I chose the 1 liter because it is just a nice number. Actually, it's not that nice because you have to convert that 1 liter. This is not the unit here is unfortunately not in volume. Yes, it's not. So we kind of have to change that to ounces. Let me change that to ounces, guys. So yeah, let's just go with 33 ounce. Yeah, I kind of have to. Oh, I can't. Okay, I can't change it to ounce either.
Why do you change, Professor? Why you don't use?
Because yeah, I don't like the liter here. I really don't. I don't like liter. Let me change that to. So in centimeter cube, let's just change it to. Hold on. Give me a second. Let's just change it to 1,000. Yeah, 1 liter is 1,000 cubic centimeter. Yeah, I was gonna change it to. That makes more sense. So, that's 1,000 cubic cm. Because the liter doesn't have a unit of cube. It doesn't have cubic units, so I like to change it to cubic unit. It's easier that way, trust me. Because I think at some point we're gonna involve cube roots, so this would be a good option. Anyway, let's do it. So here is the picture. It's just a cylinder, nothing crazy. I don't even need the picture. All right. And okay, so guys, the important thing here is, yeah, the important thing here is that you acknowledge that this is a closed, so we kind of have to be careful here. It's a closed cylindrical can, which means that the bottom as well as the top are included. All right, so keep that in mind. All right, so let's see what it is that we are trying to do. We want to choose the height and radius. Okay, so I want to know what this height is and what this radius is. Call that H, call this R. These are all unknown. H and R are unknown. Let me write it down. So we want H and R so that the amount of material used is minimum. Okay, that would be surface area. We want to minimize the surface area of, so that the surface area is minimum given volume is 1,000. We have a fixed volume 1,000. That's how much you must fit. How do you choose H and R, so the surface area is minimum. So here, the objective function is the surface area of the cylinder. Not only the lateral surface area, but also the area of top and bottom. Okay, so for top and bottom, you have two discs. These are discs or circles. And the area of the circle is pi r squared. We have two of them, so it's 2 pi r squared. Okay, so this is the area of top plus bottom. Okay, plus we also need the lateral area. Now, can anybody tell me what is the lateral surface area of a cylinder? Anyone? You can conform the cylinder into a yes, Saad. Thank you. The way Saad got the lateral surface area is by conforming the cylinder into a rectangle. Guys, pay attention. You're gonna have to do this for chapter 5 actually. Okay, you need to understand this in chapter 5 most importantly because and I'm not gonna go over it again, so please pay attention. We have this cylinder. I wish I was in class, I could show it to you, but actually I can show it to you in camera. Okay, so this is the cylinder. Let me see if I could see myself over here. Cylinder. Okay, I got a bill from UPS for no reason. They sent me a wrong packet and they send me a bill for it. Okay, cylinder. All right, open it up. It becomes a rectangle. Okay, so very easy. Now, the area of a rectangle is length times width. Okay, so how do you get this length? The length of the length of this rectangle is the same as the circumference of the circle. Okay, and we know how to find the circumference. So you take the circumference of the circle and you multiply by the height of the cylinder, which becomes the width of the rectangle. That's how you get the surface area of the lateral surface. Okay, I'll show it to you. So again, if I cut this open, I'm cutting the cylinder open. This is H, okay, and this is 2 pi r, circumference of this circumference right here. So maybe if I draw that in blue, here, I'm gonna draw this circumference for you in blue. That is the same as this length right here. Okay, so length times width is 2 pi r times h, the lateral surface. 2 pi r times h. Okay, and I'm gonna call this S for surface area, or you can just call it A if you want. Let's just call it A. A is fine. This is our objective function. Again, this objective function is a function of R and H. It requires multivariable calculus. If you take that course, you could probably answer the question without trying to eliminate variables. You have to use the method of what's called Lagrange multipliers. That's one method. Or you can try to eliminate one of these variables, okay? And for that, we have to use our constraints. So here the constraint is the volume. It's how much you are limited to fit, okay? This is our constraint, volume being 1,000. Volume is limited to 1,000. So volume of the cylinder is pi r squared h. Again, this is the volume of cylinder. Pi r squared h must equal to 1,000. That's our constraint. This is just like the farmer problem. Let me go back to the farmer problem for a second. For the farmer problem, you're also trying to optimize the area function given that the perimeter is equal to 100. Optimizing that, given the perimeter here, you're optimizing area. We're optimizing area given this volume. Okay, so this is a higher dimensional problem. What does this volume equation give us? Again, if this is relating, this is an equation that relates R and H. And you can solve this equation for either R or H to plug in here to make this an equation of only one variable. Now, what do you solve for? It's up to you. Totally up to you. If I solve this equation for H, all I gotta do is just divide by pi r squared. Okay? But if I solve this equation for r squared, I would have to take square root, and that can make things a little bit more complicated. I don't want to do that. So just solve for H. H is 1,000 over pi r squared, and plug into objective function. Okay, so our objective function becomes a equal to pi r squared, and then times or plus 2 pi r squared plus 2 pi r. This h is now 1,000 over pi r squared. Okay, so again, this goes in here. Okay, and look at that. You only have r. Let's simplify our objective function. This function is now just a function of r. It's a of r, which is 2 pi r squared plus, here the pi's cancel. One of these r's cancel out. You end up with 2,000 over r. Okay, and look at the degree of this function. The degree is, well, it's not a polynomial, first of all, but the degree here is 2.
It's pi r or just only r, Professor?
What is that?
2,000 over pi r or just only r?
Pi's cancel, didn't they? Here, these pi's cancel out. Right? Don't the pi's cancel? Am I missing something? Okay.
No, yeah.
You scare me sometimes. Why would she ask that question? I did something wrong. She's so smart. Okay. All right. So again, y is the degree here too, guys. Y is the highest power too. Anybody? Should it be 2? It should, right?
It's area.
It's area, exactly, area. It's just that this term could bug us a little bit. This can bug a little bit because we have divided by r. So you're like, oh no, that's not continuous. So what do I do? Nothing. You're fine. Yeah. So do I want to get the domain of this thing? Let me see here. Yeah. The domain you might have a little bit of a problem with the domain, but this is a function of r. So you got to think about it a little bit. How can I choose r? What are legitimate values of r over here, guys?
Except 0.
Except 0. R can't be 0 for sure, right? It just makes no sense. R can't, of course, be negative, and that makes no sense. But can I choose R any other way that we want? Like how small can I choose R? I can choose R as small as I want. I just can't choose it to be 0. I can draw the cylinder any way I wish, guys. There are infinitely many ways that you can draw the cylinder. You can make R 0.1, but then to fit 1000, the height has to be extremely large. You know what I mean? It's a stupid looking can for sure. No one would do such thing. Okay, it's really dumb to do something like that, but you can theoretically do something like that. Okay? Who said you can't choose R to be 0.1 or 0.01 or 0.001 or infinitesimally small? You can. Or you can make R as big as you want. For the same reason, I can make R to be like, let's say 100. I can make R to be 100, but then I have to make height very small if I want to fit 1000 cubic centimeter of stuff in there. Again, it doesn't look good. Or I can make R equal to 100 and make the height really, really, really small to fit 1 liter. That doesn't even look like a cylinder. I can make R 100, but the height has to be really small to fit 1000 cubic centimeter cm. You can do all of that. I mean, it just doesn't look natural, but theoretically it's possible. It's just like the rectangle that I was talking about yesterday. Where is it? Oh no, the rectangle, you're limited on that actually because you have only 100 feet of fencing. But R can be anything but negative or 0. Okay, that would be the domain of this function. So domain R is just positive. R could be anything. You can make the cylinder look as ridiculous as you want. It's just that, I mean, just look at this function, guys. Look at it. This is a rational function. R can't be 0 because it makes the denominator 0. And logically, R can't be negative because it's dimension. Okay? All right, well, let's differentiate this function. Find a prime of R. The derivative of 2 pi r squared. 2 pi is a constant. Bring the 2 in front. You get 2 times 2, 4 pi r. Please don't do dr dt, okay? We're not looking at related rates. And then I hope by now you guys can do the derivative of 1 over r. That's the same thing as r to the negative 1 2000 r to the negative 1. Its derivative is negative 2000 r to the negative 2. You can reciprocate that to over
Professor?
r squared. Yeah.
Why can't it be 0? Because I know yesterday you were including 0 in the domain, and you
Right.
said that
I got
volume can be 0.
Well, okay. So look at this function. Look at that function. Can you put 0 into r? Can I put 0 here?
No.
No, I can't. But let's go back to one of the other functions. Like for instance, something as bad as this function, okay? H here is the variable. Can you put 0 for h? Does it make it undefined? Do you see an do you see an h in the denominator? Capital H is just a number like 10, but in this variable, am I allowed to put 0? Does it make it undefined?
No.
No. Okay, let's
I
go
think
back.
what was confusing there is that there was a big H and a little h, so.
I know. Again, did you do this, Josh, with choosing numbers for h? Did you redo it? You should do it. Okay, what about this one? Over here, this objective function, the variable is y. Can you plug 0 here?
Yes.
I can. It doesn't make it undefined. Or here, this polynomial, can x be 0? It can. It doesn't make it undefined. But here we can't. I can't make r equal to 0 because volume is just gonna become infinite. Volume will become infinite. If you put, see, if I put 0 here, then this thing becomes infinity and you have a infinite area. And that just makes no sense. All right, so this is the derivative a prime of r. And then we set this equal to 0 to find our critical value. Okay, and just solve this equation has r squared in the denominator. Just multiply everything by r to get rid of the fraction. Here, multiply by r squared. I'm gonna get 4 pi r cubed minus 2000 equal to 0 times r squared, that's 0. And then you can isolate r cubed. R cubed is equal to 2000 divided by 4 pi, and that gives us 250 over pi. And then take the cube root. Do I have that right? Yeah. Oh, wait. Is that right? No, it's not.
Not Professor.
No, I'm sorry. Yeah, what's 500? This is why I don't teach basic math, because I can't divide or multiply. I really can't. And my kids are gonna have such a hard time with their arithmetic homework. I just can't do arithmetic. And then just do cube root.
You have 1 0 extra, Professor.
See, I told you. Okay, cube root of 500 over pi. And I'm not joking here. I'm not kidding. Okay. Let me see.
You are good for payment, Professor.
And what?
For payment, your employee put extra 0 on the check.
Exactly, right? Okay. And that's it pretty much. That's my R. Now, if you want to get this numerically, let me see here. If you want to do this numerically on the calculator, you just do 500. You don't have to, because you can just leave the answer in exact form. That's 500 to the 1/3 power, 500 over pi. To the power of 1/3, that's equal to 5.4 approximately. Just to get an idea, and it's in centimeters, just to get an idea. Okay, now, the thing is that we need to show that our function has a minimum at this point, okay? That's what you need to do. Show that this is minimum. All right, so guys, I have been, for all the problems, I have been plugging endpoints and the critical value. And if it was a minimum problem, I would take the smallest, like the last problem that we did, it was this one right here. I plugged the endpoints and the critical value. This was a minimum problem. I took the smallest. Okay, for other problems, this was a maximum problem. I plug in the endpoints and the critical value, and I took the biggest. Of course, this is the biggest. So the question is, well, what do you plug in? Because I don't have endpoints right here. R greater than 0, well, I can't plug 0 into my objective function right here. I can't. But what you can do is, since you can't plug 0 in, you can take the limit as x goes to 0. Okay, that's one option that you can do. What would happen if you do such thing? This would go to infinity. Just use logic. Surface area would go to infinity. If I make this r really small, then the cylinder is just going to become big, right? And the surface area gets bigger. So this thing, mathematically, it does go to infinity as r goes to 0. Okay? And between infinity and 5.4, well, 5.4 is smaller. Okay? Now, if you don't like any of that, there is another option to show that this is going to give you minimum, and that's by using the second derivative test. For all of the other problems, you can also use second derivative test. I've been saying all along, you have both options. So if I want to show that this is minimum, then I need to show that the function is concave down. I'm sorry, concave up. Concave up means that at the critical value, we have a minimum. So what you need to do is differentiate this again. Okay, find a double prime of r. So the derivative of that is 4 pi. Okay, and then differentiate this guy, differentiate r to the -2, r to the -2, r to the -2. The -2 goes in front, it makes this a positive, and then that 2,000 becomes 4,000, and then you have r to the power of 3. Okay, so again, I'm differentiating this term right here. That term is -2,000, r to the -2. Bring the -2 in front. You get positive 4,000, r to the power of -3. And then when you reciprocate that -3, you get positive 3 in the denominator. This is the second derivative. And look at the sign of the second derivative. if I were to plug in my critical value or any positive value for R, if I plug 5.4 into R, I'm going to end up with a positive second derivative. You don't need to really plug in because these terms are both positive, which means that the function is concave up. It's concave up. So here A double prime of 5.4, or you could just leave it in, you can leave the critical value as is. This is greater than 0. Again, guys, you don't need to plug it in for me because it is pretty obvious. Positive, positive. Whatever I plug in for R, it's positive. Therefore, A has minimum when R is equal to cube root of 500 over pi. Okay, so that's what you choose your R to obtain the smallest surface area. Okay? Good problem. This is a really, really good problem, honestly. Again, another highly applicable problem. When you move on to calculus 3, I don't think you do related rates much, but you'll definitely do optimization in calculus 3. So make sure you guys don't forget this stuff, please. Even after the summer session, you guys should review optimization. There are a couple of things you need to review when you are done with Calc 1. One is optimization, and the other is antiderivatives, which we're gonna start today. Okay, and then last problem. These are one of my among my favorite problems also. Number 6 has got to do with minimizing distance from a path to a point. Yes, Carlos, you can for sure use first derivative test. Definitely. Up to you. So this problem says, find the point, or it says a point, I don't know why. Find a point on the curve y equal to x squared that is closest to 18, 0. Okay, so let me draw this figure. We have a path, we have a parabola, y equal to x squared is this graph. And we have a point. So on the x-axis, we have this point. Let's just say this point, which is 18, 0. And you want to find the shortest path from this point to the parabola. There are many ways to go from 18, 0 to this path. If you've taken pre-calculus, you've probably seen this type of problem. But imagine you are located, or you're stranded at this location. Okay, this is like, let's say, some desert, and it's really hot. You're about to die. You have no energy left. Okay, and this is a road where cars kind of drive on. Okay, so this is where you want to go to save your life or whatever. Okay, trust me, if this happened in reality, you would do calculus in your head. People become super people when they're in very stressful situations. Your brain naturally finds a solution. It does. It's really cool. But there are so many ways that you can walk from this location to this road. Okay, you could go this way, you can go this way, you could go that way to get to the road. You could go just directly west to get to the road. But one of them is gonna give you the smallest distance. Okay, so to me, it seems that this would be the smallest distance. This is definitely not the smallest. This is like 18. If you take that path, you have to walk 18 units. If you take this path, it seems to be smaller. Okay, so we want to know where that point is exactly on the parabola. This is definitely an optimization problem. You want to minimize distance. Okay, so the objective, minimize distance, the distance between the parabola and point 18,0. Okay, so let me choose a point, just choose a random point on the parabola, like say this one. I don't know the location of this point. I don't know where this is. So what do? Like all other problems, here the question is, what is the radius? What's the height? I called that R, I call this H, those are my unknown. Or over here, same thing. These are my unknown, I use letters. You do the same thing over here. We don't know what this point is, so I'm gonna call the X coordinate of that point X, and I will call the Y coordinate Y. Okay, so here you want to find, again, we want to find xy. I'm rewriting the question. Find xy such that the distance between xy and 18,0 is minimum. Okay, so we all should know the distance formula, the distance between 2 points, this distance right here. I'm gonna call it D for distance. Pythagorean theorem. That's how you find distances between 2 points. It's really Pythagorean theorem. And the formula is this. So this, I'm writing my objective function, by the way. The distance is equal to the square root. You know how when you do Pythagorean, you have to solve for one of the sides, you got to take square root of the sum of squares. Square root of the sum of 2 squares. Okay, well, what goes in those parentheses is the difference between x's and the difference between y's. Okay, so remember, it's x2 minus x1. Basically, just find the difference between the x coordinates. Will be x minus 18. And then the other square is the difference between the y coordinates. It's y2 minus y1, or just y minus 0 in this case. Okay, the distance formula. Let me write that in the notes here. Distance between 2 points x1, y1, and x2, y2 is given by this formula, square root of x2 minus x1 squared plus y2 minus y1 squared. The distance formula, that's exactly what I use. Again, this formula comes from the Pythagorean theorem. Okay, so this is our objective function, the distance function. And the thing is that, again, this function is now a function of both x and y. This is d of xy. It's a function of two variables. We don't like that. We want to eliminate a variable. So we have to use the constraint of this problem. The constraint is that this point, the constraint is on your, always on your variables, okay, on your unknowns. This x and y can't be just any xy in space, okay? This xy is the xy that is on this parabola. It should satisfy the parabola. I am not going from 18, 0 to wherever I want in R2. We're not free to just go to anywhere to catch a right, okay? We must go to this parabola. That is our restriction. That's our constraint. The constraint is that this xy should be on the parabola, which means that, remember also that the constraint is the relation between x and y. The relation between x, y, and it's looking at you right in the face. The relation between x, y is this right here. The constraint is the equation that relates your y and x. That's your constraint. Always equation relating the unknowns. And that's what we've been doing for all the problems. Look, this one. Here's your constraint. Equation relating h and r. Okay, or right here, the constraint is this. Equation relating r and h, your unknowns. Or here, the equation relating x and y, your unknowns. That's what the constraint is. And you don't have to do any math. It's just right there. I didn't have to do a triangle. I didn't have to do proportionality. It's right there. That's what's good about these questions. They tell you how your unknowns are related. So what I do is I plug this into my y. So you get d equal to the square root of x minus 18 squared plus, here x squared goes in for y. So you get plus x squared minus 0, the whole thing squared, square rooted. Okay, which simplifies to, let me add like terms, guys. Here you have an x squared squared, so that's x to the 4 plus, I'm going to square this thing out. If you square it, you get x squared. And then here I have minus 2 times 18, that's 36. X plus 18 squared. Anybody know what that is? 18 squared is equal to 324. Okay, just simplify this junk. Okay. So next, we take the derivative, or you can find the domain. But let me mention something here, guys, about minimizing, maximizing distances. there is a rule. This is a really helpful rule, so you want to listen. If you ever have a square root function, okay, and you are trying to optimize it, the solution is the same as the solution for the square of your objective function. So what that means is that I can just avoid the square root. The minimum of distance is the same as the minimum of the square of distance. That's what the theorem says. So you can just avoid the square root. I'll write the rule. Let me write the rule over here. The solution, the optimal solution for the minimum of the square of distance is also the optimal solution for the minimum of distance. Okay, so this says that d of x, distance is a function of x, and the square of it. And you could easily actually prove this. Have the same minimum. This allows you to drop the square root out. When you square it, it just goes away. I can completely ignore that square root. Okay, so again, here we can minimize, let's call it capital D of x equal to x to the 4 plus x squared minus 36x plus 324. So you might say, oh, this is a lot of information. Why? What the heck? Why is it doing this to me? This is meant to make your calculation easier. Okay, I'm giving you this rule because we don't like to take the derivative of the square root. If I can solve the problem by dropping the square root out, then why not? If you don't want to learn this, it's all right. It's totally fine. I'm not going to judge you. You can just go ahead and take the derivative of that. I don't care. You know what I mean? So it's just up to you. Up to you. All right, so let's differentiate here and see what we get. By the way, do you guys want to work with that? Let me see. Which is easier to differentiate here? Is it easier to differentiate that or this?
Last one.
This one, right? So, okay, why not? Let me just keep it this way. X minus 18 squared plus x to the 4. Yeah, I'm just gonna leave it like that. I'm hoping this thing does have a nice solution. Okay, so I'll just leave it. Drop the square root, guys. Whenever you have distance between a point and a curve, just drop the root if you want. If not, then fine. That's fine with me. Okay, so let's take the derivative. The derivative of this function is 2 times x minus 18. Okay, just use chain rule, bringing that 2 in front. The derivative of x minus 18 is just 0. Oh, it's actually 1. Plus the derivative of x to the 4 is 4x cubed. Okay, and yeah, I'm afraid this might have a, yeah. I'm trying to set this equal to 0 to find critical values. I don't like cubic equations, guys. I don't. Okay, but all right, it's fine. It's all good. Okay, so we want to find critical values. You want to solve this equation. First of all, if you notice this equation, if I were to multiply the 2 in, or if not, this equation has a 2 in common. 2 is a GCF. Here you have a 2. Here you have a factor of 2. You can just divide 2 out and get rid of it and write this as 2x cubed plus x minus 18. Actually, yes, equal to 0. Okay, so that's our equation. It's a cubic equation, as I said. I don't know where I got these problems from. I have no idea. But the question is, how do I solve this equation? Okay, so if this was quadratic, I could have used the quadratic formula. But I want you guys to remember certain things from pre-calculus, the rational zero theorem. This was actually a question on your first exam where you had to factor out the expression. But the question is, what is a possible root of this equation? What do I plug for x to get 0? Okay, well, you can begin doing a lot of algebra, or you can try numbers out. Try to please be as logical as you can. How do I solve? You could solve by inspection. Just begin plugging values into x, please. Notice that my x from this picture is really helpful. X is definitely not negative because x is right around here, okay? So 0, I mean, if I plug 0 here, I get negative 18. That doesn't give me a solution. So just plug like, let's say 1, 2, 3, and so on. See which gives you a 0. And again, try to be reasonable here. Don't pick like 19. 19 is too far. It's over here. Let's pick 2 and see if I get a 0. So 1, if I plug 1 in, I get 2 plus 1, 3 minus 18, that's not 0. If I plug 2, I hope that works. Does it? If I plug 2 in here, 2 cubed is 8. 8 times 2 is 16. 16 plus 2 is 18 minus 18. That gives me 0. Solve by inspection. Typically, this type of equation happens a lot in calculus, where in this book, where you can just solve by inspection. You don't need to go crazy, okay? By observation or by inspection. We get x equal to 2. Okay, so 2 is a 0 of this equation. All right, now you want to know if there are other solutions. Okay, you could try to factor this out, do the rational zero theorem. So other solutions. That's the question. You don't have to do this. I think 2 is it. But to check for other solutions, you can do a synthetic division. I know 2 is a root, okay? So what I do is I take the coefficients of this polynomial. The coefficients are 2. That's the coefficient of x cubed. this doesn't have an x squared. So the coefficient of x squared is 0. The coefficient of x is 1 and the constant -18. Bring the 2 down. Multiply by 2, you get 4. 0 and 4 is 4. 4 times 2, 8. Plus 1, that's 8, 9. And then 9 times 2, 18. I get 0. And I should get 0 because 2 is definitely a root. 2 is a root. Okay, so this equation here becomes, in factor form, x minus 2 times 2x squared plus 4x plus 9. Okay, these coefficients are these numbers that we have obtained. Okay, equal to 0. So I wrote this equation in factor form. Now you want to know if there are other solutions. So what you do is you try to factor this out again. Or you can use quadratic formula on this to see if there are possibly other solutions. Sorry, it's kind of getting a bit crowded here. Yeah.
It's 4 or 6. And instead of 4.
Where, here?
Yes.
Bring the 2 down. 2 times 2, 4. 0 plus 4 is 4. Why would I get 6?
We have to subtract or we have to add them here.
I added them. So bring the 2 down. You get 2. Multiply by 2. You get 4. Add 0 to 4. You get 4. 4 times 2, 8. Add them. You get 9.
Thank you.
Yeah, that's the synthetic division. Okay, so see if this thing has other solutions. You could do the quadratic equation. X is negative b plus or minus b squared is 16 minus 4 times 2 is 8 times 9. That's 72. This is great news because I get a negative discriminant. This thing is negative. This doesn't have any more real solutions. So x equal to 2 is the only solution, and I could just move here, is the only critical value. Okay? Yeah, and then let's just go ahead and do our second derivative test. If you don't want to deal with the domain and all that, just go ahead and do our second derivative test. You can take the double derivative. So here again is my derivative, or you could take this form, it doesn't matter. Take the derivative of that again. D double prime of x is equal to, right there, the derivative of 2x cubed is 6x squared plus the derivative of x is 1, and the derivative of negative 18 is just 0. And I don't need to go any further because this is a sum of 2 perfect squares. Well, this is not perfect, but this is a sum of 2 squares. And this thing is always positive. It doesn't matter what you plug in. I can plug 2 in. See, d double prime at the critical value is equal to 6 times 2 squared plus 1. I don't care what that gives me. This is positive, which means that d double prime is, which means that d is concaved up. So at x equal to 2, our distance function has an absolute minimum. And that's what we wanted. We wanted to minimize distance, and we did. So if I if you choose x equal to 2 on this parabola, wherever that is, the distance is going to be smallest. Okay, so what would that point be? It would be the 0.24. 0.24 gives you the smallest distance. Yeah, on the graph of y equal to x squared, yields minimum distance to the point 18,0. So if you're ever gonna go hiking in a desert, take your calculator with you. You just gotta know where the road is. All right, let's take a break. Yeah, so antiderivative is just the name should kind of explain itself. You're doing basically the opposite of a derivative. Give me a second, guys. Oh yeah. So so far we've been just doing differentiation, applications of differentiation, related rates that have to do with derivative as time changes, and graphing that has to do with basically analyzing a function, and that's done by looking at the first derivative, second derivative, optimization, where you find the optimal solution where the derivative is 0. That gives you the absolute max, absolute min, and all that. Now we look at antiderivatives. Let's say that in application, you measure the rate of change. So question is, a good question would be, given that we know the rate of change of a function, so this would be dy dx. You know the derivative. So like, let's say you have a chemical reaction and you measure how fast, let's say quantity changes, how fast the amount, the weight of a certain, like let's say chemical compound changes. The question is, how do you find amount? You know how fast amount changes, how do you find amount itself? So here you're given dy dx. Question is, what is y? You have the derivative, you want to retrieve the function itself. Given the derivative of a function, we want to find the function. Does that make sense? You're going backwards, basically. You're doing the opposite. We're going to be doing the opposite of the derivative. Okay, so let me define what an antiderivative is. It's the definition for antiderivative. So here we say, and I'm going to refer to antiderivative of a function as capital F. So here we say that capital F of x is an antiderivative. Now I didn't say, I'm not saying here it's a D. Let me take attendance, guys. By the way, I don't forget that. Go ahead. Attendance form. We say that capital F of x is an, so when I say it's an antiderivative, it means that there could be multiple antiderivatives, multiple. It's an antiderivative of little f of x if I take the derivative of capital F to get little f back. This is the definition of an antiderivative. I'll show you an example. So what this says is that the derivative of the antiderivative gives you the function back. That's what this says. Here, I'll use a prime for that notation, for that thing. So this says that the derivative of, and let me use blue for capital F, the derivative of an antiderivative of a function is the same as that function. So what this says is that the derivative and antiderivative basically do opposite things. Does this make sense? If this doesn't, please let me know. So here, example, let's say I have f of x equal to let's say x. Okay, let's just focus on a simple function. Okay, so an antiderivative, let's just do part A. And I'll show you how to find antiderivative. An antiderivative is, call it capital F. It's equal to half x squared plus 4. Okay, well, why is that? Just go based off of the definition. This is because if I take the derivative, I am taking the derivative of capital F, that's d dx, of here our capital F is half x squared plus 4. Okay, when you differentiate x squared, you got 2x. It cancels the half. Look, 1/2 times 2 times x plus the derivative of 4 is 0. What do you get? You got x back. Okay, I got f of x back. So this thing is an antiderivative. It's an antiderivative. It's not the antiderivative.
You're saying and because that 4 could be any constant?
Yep, exactly.
Okay.
Here is another one. Another antiderivative is capital F equal to half x squared plus, let's say, 15. Again, that's because if I take capital F and differentiate it, I get half x squared plus 15, same as before. You get 1/2 times 2 times x. If I bring the power down, subtract 1, plus the derivative of 15 is 0. And again, I'm going to get, just like before, x back. I got f of x back. The derivative of capital F gives you little f. As long as that happens, you get an antiderivative. Okay. There are, as you see, there are multiple antiderivatives. This is not one of them. Because this number could be anything. Okay. I could have any number, any constant as a term for this antiderivative. And the derivative of that constant is always 0. So as long as I have this piece plus a constant, I have an antiderivative. Okay? So what this says, as you see, note that f of x, capital F of x, equal to 1/2 x squared plus any constant is an antiderivative. It's an antiderivative of f of x equal to x. Okay, because the derivative of that gives you always that, since the derivative of c is just 0. Okay, so again, the rule here, or call it theorem, which says that if capital F of x is an antiderivative of little f of x, then capital F of x plus whatever constant of your choice is also an antiderivative. I have a little f. This constant has a name. It's called a constant of integration. We'll see why. I don't know if the book defines that yet, but that's what it means. That's what it's called. The constant of integration, where c is any constant. Okay, does that make not make sense to anyone? Does this not make sense to anybody? The derivative of c is simply 0, so you get f, little f back, no matter what c is. Okay. Yeah, so let me show you how to find antiderivatives. Okay, and we are doing exactly the opposite of derivative. Okay, so if you are given a function, listen to this. If you're given a function and you are asked for the antiderivative of that function, so for instance, like let's say you're asked to find an antiderivative of, like, let's say, I don't know, x squared. Okay? This is what you ask yourself. The derivative of what gives us x squared? Okay, so here little f of x is equal to x squared. We want capital F of x. Okay, we want this capital F so that the derivative of capital F such that st here means such that if I differentiate capital F of x, I get I get x squared. Okay, so you're asking, we are always asking ourselves the derivative of what is equal x squared. You gotta we have to kind of think backwards. Okay, so when we took the derivative, we subtracted 1 from the exponent. Here we do the opposite, and obviously it should be x cubed, right? See, I am looking for the derivative of something here, that question mark, something that gives me x squared. Yeah, Carlos, excellent. Yeah, so the power of this antiderivative should be x cubed. It should be x cubed. Okay, well now you are like, okay, if I take the derivative of x cubed, I am gonna get actually 3x squared. I don't get exactly x squared. I got the x squared part right, but I get 3x squared. There's an extra 3. So what I have to do is really divide this thing by 3 to cancel that 3 out when I take the derivative. Okay, so there should be a 1/3 in front over here. Okay, now it checks out. If you differentiate this thing, the 3 goes in front, you get 3 divided by 3, it cancels out, you have 1x squared. Okay, so that's how you have to kind of think, but I will give you the power rule. Well, we're gonna look at the power rule for antiderivatives. And again, we could have a constant here, right? Because the derivative of that constant gives us 0, so I would add that constant anyway. So here our capital F is 1/3 x cubed plus c. And you can check the derivative of that gives you x squared. So we can write down our first rule for antiderivatives just the way we wrote down the first rule for derivatives. It was the power rule. Okay, so remember the power rule for derivatives said that derivative of x to the n, and we proved it, is equal to n x to the n minus 1. Power rule for derivatives. Power rule for antiderivatives says that if little f of x is some power function x to the n, then an antiderivative, capital F means antiderivative, is going to be x to the n plus 1. Again, we are doing the opposite. For power rule for derivatives, we took away 1. Here we add 1. Okay, as we did right here. See that? That's a 3. But then you have to, but then if you check, if I take the derivative of this to see if I get that, then I get an n plus 1 in front. That's not good. I don't want that n plus 1. So what I do to compensate, as I have done here, divide by that new power. You divide by n plus 1. Yeah, plus some constant. constant here is, again, the constant of the antiderivative. Okay? The antiderivative of x to the n is x to the n plus 1 divided by n plus 1. All right, now this formula, this antiderivative function has a problem. It does have a tiny problem. It's always good. This formula is always good except for one special case. And who can tell me what that special case is? You can just look at it. Look at the antiderivative, capital F. I have a fraction. So n is restricted.
Oh, if it's raised to the power of 1, maybe?
Negative
No, never
1.
mind. Negative
Yes, yeah, exactly, Saad. And Catherine, it should be n equal -1. If n is -1, then I get -1 plus 1, and that denominator is 0. No good. Oh, it's okay. I know what you meant, Catherine. But yeah, this would not work for n not equal for n equal to 1. Yeah, it wouldn't work. So here I would say where n is not 1, it works anytime for except n is equal to -1 and n is not equal to -1. N equal to -1 is a special case that you guys will deal with in calculus 2. Yeah, see, when n is -1, our function f of x is f of x equal to x to the -1 or 1 over x. This function 1 over x is a special function that will be studied in calculus 2. So this has a special antiderivative. Meaning that basically the power rule does not apply. The antiderivative of 1 over x happens to be the natural log of x. And we are not dealing with logs in calculus 1, so wait till you get to calc 2. But this formula works for whatever n, any other n except for 1. Okay, so the proof again, the proof of it is very easy, very easy. If you want to prove this rule, all you got to do is show that the derivative of capital F gives you little f back. And it's pretty obvious. When you take the derivative of this thing, the n plus 1 goes down. You get n plus 1 over n plus 1. They cancel out. And you take away 1 from that power, so you end up with just x to the n. I ended up with little f. Very simple proof. If you want to show capital F is an antiderivative of little f, you take the derivative of capital F to show that you get little f. Derivative of that gives us that. Okay, so examples. Let's say we are finding antiderivatives. So let's say little f here is x to the power of 10, capital F, add 1 to that power, and you get x to the 11, divide by the new power, 1 over 11, or put 1 over 11 in front. So 1 over 11, x to the 11 plus some constant is an antiderivative of x to the 10. Okay, power rule. Or like, let's say here, g of x is equal to square root of x, or x to the power of 1/2. Capital F, or capital G, I should say. Add 1. to that power. Here, let me just write it down. 1/2 is the old power, add 1 to it. And now you divide by that new power. 1/2 plus 1 plus some constant. Okay, so here what we get for capital G is 1 divided by 3/2 times x to the power of 3/2 plus some constant. Here you have 1 over 3/2, so you could just flip 3/2 to 2/3 and put it in front of x to the 3/2. Okay, this here is the antiderivative of square root of x. Okay, if the power is a fraction, so the way I do this in my head, I have x to the 1/2. What I do is I add 1 to that in my head. I get 3/2. Multiply by the reciprocal of that, which is 2/3. We always multiply by the reciprocal. See, this is 11. You multiply by the reciprocal, 1 over 11. This is 3/2 multiplied by the reciprocal, which is 2/3. Let's just do one more. Let's say capital a little h of x is equal to 1 over x to the 5. Then capital H, well, okay, I can write that as, write your function as a power function. 1 over x to the 5 in power form is the same as x to the -5. And then do the antiderivative business called capital H. Again, I am going to add 1 to that power and divide by that new power plus some constant. So here, capital H is equal to -1/4 x to the power of -4 plus some constant. Okay. Power rule. All right. Okay, let me see. How far deep do they get into this stuff here? Man, give me a second. This section is just so inappropriately fitted into chapter 3. Very inappropriate, very. Yeah. Let's look at the antiderivatives for sine, cosine. Oh man, I really hate writing capital F and little f. But if little f of x, so other examples, actually just rules. Let's say little f is sine x. We want to know the antiderivative of sine x. Capital F. Okay, so you ask yourself, the derivative of what gives me sine x? Well, you know that the derivative of cosine x is, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Okay. So you ask yourself here, what do I do? What do I take the derivative of to get sine of x? Of course, the answer is cosine x, but let's check. Let's check. If I do f prime, if I take the derivative of cosine, I end up with negative sine of x. I don't end up with sine x itself. I have a negative in front. And I don't like that. I want that negative to go away, cancel out. So what I do is I put a negative in front of that. Now, when you differentiate the negative of the derivative of cosine x, which is negative sine x, gives you positive sine x. Okay, so antiderivative of sine x is negative cosine x. Okay. Likewise, if f of x is cosine of x, the antiderivative of that, and don't forget the c, the antiderivative of that is just sine of x plus some constant. Check. If I take the derivative of sine x, I get cosine x. I get little f back. Okay, if f of x is equal to secant squared x. So why did I go with secant squared x? Because secant squared x is the derivative of something. The derivative of what gives you secant squared x?
Tangent.
Tangent. We know the antiderivative of secant squared. It's tangent x. Again, you can check, take the derivative of that, you get exactly that. Okay? Or like let's say f of x is equal to cosecant squared x. Again, I'm going with cosecant squared x because it is the derivative of cotangent, negative cotangent. Again, you can check the derivative of cotangent is negative cosecant squared, but this is a positive, therefore I need that factor of negative. Okay, and we got two more. The next one is secant x, tangent x. You're like, wait, why is he choosing such hard functions? Because secant x, tan x is the derivative of what? It's a derivative of secant x. You can check. If you do f prime, capital F prime, you get the derivative of secant x, which is secant x tan x. So the antiderivative of secant x tan x is just secant x. Last one, if f of x is equal to cosecant x, cotan x, its antiderivative is negative cosecant x. Okay, now you might say, hey, what is the antiderivative of tan x? Let's see if we can find that. Someone asks you, little f, the function is tangent x. So what is capital F equal to? Well, you ask yourself, this is what I do in my head. I ask myself, the derivative of what is equal to tangent x? Knowing what we know from calculus 1 so far, can you really answer this question? Can we? We really can't. Really can't. These are the only antiderivatives we really have. Okay? We have the derivative of cosecant x, which is cosecant cotan. The derivative of secant is secant tan. The derivative of cotangent is negative cosecant squared. None of these are tangent. We really can't think of such function. We really can't. If you look at the list of your trigonometric derivatives, let me go back to my derivative of trig functions. Here are my notes. I think I summarized them. Yeah, nowhere in this list I can find a function that gives me a derivative that's equal to tangent. Okay, so here we begin with this. Derivative of sine x is cosine x. See, this didn't give me, this is not equal to tan. I'm looking at the outcome of these derivatives. This is not tangent. I want to know what the derivative of what gives me tangent. Right here, this is secant squared. I'm looking for a derivative that gives me a tangent. I'm looking for a derivative that gives me tangent x. None of these derivatives are equal to tangent x. None of them. This is tangent. This comes closest, but this is tan secant. This is cotangent. So we can't really think of such function at this point. Trying to think backwards, we just can't. Cannot. Yes, we can't. Finding antiderivatives, guys, is really hard. Okay, it's not like finding derivatives because you have to think backwards. There are really not a lot of rules for antiderivatives. There is not. We don't have like product rule, chain rule, any of that. You kind of have to really think backwards in most cases. So keep that in mind. Finding antiderivatives, thinking backwards is not easy. Okay. Yeah. So this is a math 8 question, finding antiderivative of tangent. Okay. All right, so I am kind of, I don't like keep writing little f and capital F. I don't. I want to use a notation for antiderivative. I'd like to use an antiderivative. You know how you take derivative? It's d dx, the derivative of some function. I have a notation. d dx means derivative. So what is the antiderivative notation? The book doesn't introduce that notation yet, but I'll do it anyway. I should have done this earlier to save some time. This is a weird notation for now. It's weird and it can get really confusing in the next section, but it's just a notation. Okay, so instead of writing antiderivative of f of x, okay, we use the following notation. F of x. So if it's derivative, it's d dx. If it's antiderivative, then it's the stretched s notation. It's a stretched s in front of f of x, and then you put a dx right there. This is read as antiderivative of f of x with respect to x. Instead of like doing d dx, you put the dx in front. Antiderivative of f of x. Hold on a second. Let me use different colors. I'm going to use blue for f of x. And then with respect to x. So dx here is what it means with respect to, oops, hold on. Again, the s notation, the stretch s notation means antiderivative. Then you say f of x, and then dx means with respect to x. And there is a reason they write it like that. This S kind of has to do with sums, with addition, with sums. Antiderivatives at some point next week we'll learn it has to do with summation. But that's what this means. So this dx, I know that you know this as a differential, but this dx means that again, you're doing this with respect to x. You are doing antiderivative, anti-differentiation with respect to x. The variable here is x, is why they call this dx. Okay, so for instance, if I want to use this notation, instead of keep writing little f and capital F, which is kind of annoying, I will say the antiderivative of sine of x dx is equal to negative cosine of x plus c. Because again, the derivative of negative cosine gives you sine. Questions, guys?
Yeah, Professor.
Yeah.
I was gonna ask, are the sine or cosine or those derivatives ever gonna have a constant in front where we have to take like the antiderivative of that with a constant?
Oh yeah, so sure, for sure. So you're saying, what if you have sine of x plus 1 right here? Like sine of x plus some
Or more
constant?
so like,
And you have,
or just like 4.
okay, got you. All right, yeah, let's get to that. Okay, so by the way, this also has another name. It's called the definite integral. The definite integral of the function, aka the definite, indefinite, not definite, indefinite integral of f of x. Or by default, just the integral of f of x, the integral of f. Integral of f means antiderivative of f. Okay, so we'll use those terminologies interchangeably, but okay, so I'm gonna write down the rules. Unfortunately, book didn't mention these rules for definite integrals or antiderivative. Or in, just say integral properties. Just like derivative, these properties are exactly like derivative properties. Let's go back to section, I don't know what section it was, right here. Okay, this was section 2.3 where I went over derivative properties. Let me show you some stuff. Right here, for instance, this says that if you have the derivative of some constant times a function, you can just put the constant out times it by the derivative of the function. Or if you have the derivative of two functions being added or subtracted, just take the derivative of each and add, subtract the result. Okay, and we were able to apply those rules to find antiderivative of, like, let's say, expressions with multiple terms. We just ignore the constant, put it in front, and all that crap that we learned. Same rules apply here, okay? Which says that if I have the, if I have the antiderivative of some constant times a function, I can just put the constant out of the antiderivative. The derivative of a constant times a function is constant times the derivative of the function. Same thing here. Antiderivative of constant function is constant times antiderivative of the function. The addition subtraction properties say that if you have the antiderivative of a function, if it's a plus, then you add. If it's a minus, subtract. Another function, call it g of x. Then I can just take antiderivatives individually. So do antiderivative of f with respect to x. Add if it's an addition, subtract if it's a subtraction to the antiderivative of the other function, which is g of x. Okay, so these are called, again, these are called linearity rules. Linearity. Applying, if you can apply the operator to a sum, and if you could pull constants out of operators, then we say that the operation is linear, okay? Or it's a linear transformation. You get to math 13, you'll see exactly what I mean. Yeah, so I can use these rules if I see multiple terms. Let me also talk about the antiderivative of a constant. So if I have the antiderivative of just a constant with respect to x, again, don't think too hard. You ask yourself, for instance, the antiderivative of 5. I ask myself, the derivative of what gives me 5? Anybody?
5x.
Yeah, 5x plus c. 5x, because the derivative of 5x gives me just 5. Therefore, the derivative of c with respect to x is just c. Uh-oh, I'm going to have 2 c's. Okay, so let's make that a, or a constant. It's a x plus some constant of integration. That's a constant of integration. C is the constant of the antiderivative. Okay. All right, so let's see some examples here. Let's say I am to find the antiderivative of, let's say, 5 times the cube root of x plus, let's say, 10 sine x minus, let's say, 4 over x squared. Imagine you're taking derivative. We have to apply the antiderivative to each of these. Okay, so let me just take our time over here. So what I'm gonna do is, and you guys can completely skip this step, okay? You could do that because it's just pointless. It takes a long time, but I'm gonna write it down just this one time. So what we do here is, I'm gonna apply the antiderivative to that 5. And I'm gonna write that, if you don't mind, as x to the 1/3 as a power. So we take the antiderivative of that plus, and again, I have this constant now, which is sitting in front of the function. Let's pull that out at the same time. I'm gonna pull that out right here, out of that antiderivative. Same thing with this function. 10 is a constant. I'm going to leave 10 out of the antiderivative and do antiderivative of sine x. Okay, minus, same thing. Put that 4 out and write that over x squared as x to the -2, so you can use the power rule. Okay, we are applying the antiderivative operation to every piece and using this property. Okay, so for the first integral or antiderivative, use the power rule. You add 1 to that power, and then you're gonna divide by that new power. So guys, please skip the step, and you can just go ahead and do the antiderivative. Okay, so that takes care of the first piece, plus 10 in front. The antiderivative of sine x, we learned that this is negative cosine x. Oh, by the way, each of these have a c, right? We have a c. Okay, so let me not forget that. So I took this antiderivative, therefore there is a c. The constant of integration. Let me write that in red. That's not red. So plus c. And then, okay, so that takes care of that. Then we have this plus. So plus. Okay, so again, guys, 5 times that antiderivative plus some constant for this antiderivative. This guy, again, 10 in front. The antiderivative is negative cosine. Again, this antiderivative is itself going to have another constant. So plus c. Now, since these are two different antiderivatives, then these constants are different. As Berkhan says in there, yes, these constants are different. So call this C1, we'll call this C2. Different antiderivatives, different constants. If you don't like C1, C2, call that A, call this B, but we can do it that way. And then we have minus 4 in front. Let me write that minus 4 times the antiderivative of x to the negative 2 is x to the, again, negative 2 plus 1 divided by that negative 2 plus 1. I don't like cramming stuff. Hold on, guys. X to the negative 2 plus 1 divided by negative 2 plus 1. Okay, plus the constant of integration for that antiderivative. So call it C3. Again, these C's are different because we have different antiderivatives. Okay, let's simplify what we have here. So I get x to the power of 4/3. 1/3 plus 1 is 4/3. You just make that a 3/4. Remember that this is going to flip. This is 4/3. It flips to 3/4 with a 5 in front. Okay, plus C1. And then I have plus, actually, let's say, yeah, that's fine. Let's combine these. I have a negative 10. Okay, I can just make that plus into a minus. So minus 10 cosine of x plus C2. And then here we have 1 divided by negative 1. The power of that x is now negative 1. Okay, so you have that 1 over negative 1 times that negative 4, that makes it a plus 4. So plus 4x negative 1 plus C3. Okay, so here's the thing, guys. I'm trying to teach you. Good news is that you guys don't have to do 50-60% of what I've done here on the test or in your homework. I just want you to understand what's going on here so you can just skip a lot of these steps. Okay, these constants, we don't know what they are. They're just constants. Okay, like for instance, this could be a 10, this could be 1, this could be negative 2. They're just constants. We don't care what they are. So here I have 3 constants. I can combine them all into just a single constant. And instead of writing C 3 times, just write C once. Okay? and write that constant in the end. So let's just simplify. You have 5 times 3, that's 15 over 4, x to the 4th third. Again, I'm not going to write plus c1. I'll take care of that in the end. Minus 10 cosine of x. And then here I have plus 4 over x because of that negative 1. Now plus, just write down c. This c is all these constants combined. Okay, so when you're answering these questions, a similar question, just do the antiderivative piece by piece and write a big C at the end. Okay. Get it? So what is it that you can skip? You could totally skip this part. Okay. Just know that this property applies. And I would begin by writing these in power form. Write them in power form. You don't need to break up the integral. And just integrate piece by piece. Imagine you're doing 3 different problems in one problem. Okay? Yeah.
Wait, why can we combine all of them into a constant c if all of the constants are separate? Like they're not going to be the same one.
Okay. Imagine the C1 is 2. Imagine the C2 is 4. And imagine C3 is 7. Okay? So if in the end, if I were to simplify my answer, I would do what? I would do 2 plus 4 plus 7, right? That would give me what? 13? That gives me 13. Is 13 a constant itself? Yeah, so you got it. The 13 is a constant. Yeah, 13 is a constant. It's just, why would I just write all 3 separately if I can just add these constants to another constant? We can do that. We don't know what these are. All I know that if I add them up, it gives me another constant. It wouldn't be wrong if you write this 3 times, but it's pointless. Okay? All right. So a question, guys, is that how do you find the C? What the heck is the C? How do we find the C? Let me show you an example. Finding this C requires us to know a point on the curve. Okay, we need to, this is the antiderivative function. If I know a point on the function, on the graph of the function, if I know x and y, then I can plug for x and y to form an equation and solve for C. There are a bunch of problems in the book. For instance, here they say if f prime of x is equal to x plus 1 over square root of x, and f of 1 is equal to 5. See, they're giving me some information about the function. Okay, the question here is to find f of x. So what are we given? We are given the derivative of a function. We want to find the function. We're given the derivative of f. We want to find f. So what do? You do antiderivative. You do the opposite of derivative. Opposite of derivative is antiderivative. You want to get rid of that prime, do anti-prime. Okay? Yeah, so we do antiderivative. Antiderivative of the derivative of a function, remember, it gives you the function back. Okay, so again, if I want to find f of x, I am gonna do the opposite. That antiderivative is the opposite of the derivative function, and it's with respect to x. Okay, so you're given f prime. Here f prime is x plus 1 over root x. You're doing the antiderivative with respect to x. Again, the book doesn't use the S notation, unfortunately, but you can to make things kind of short. Okay, so the question is, how do I find the antiderivative of this thing? Well, we know the power rule, right? We know that we have to have term by term, and we have to have powers to do the power rule for antiderivative. So what you can do is simplify, please, this fraction. Okay, before you take antiderivative, you need to simplify and rewrite as x to the n. I want to have my terms like that so I can use the power rule. Okay, so separate. Look, we could separate this fraction or the sum into two fractions. I can do the antiderivative of x over root x, or x to the power of 1/2, plus 1 over x to the 1/2. Okay, we could divide that by that, and 1 divided by root x. Okay, separating this fraction. And then you can simplify each of these. Okay, x divided by x to the 1/2. This is a power 1, power 1/2. Subtract the powers, you get x to the power of positive half. That's when you simplify, plus that's the same thing as x to the power of negative 1/2. Okay, so I'm not doing anything yet but algebra. Now we have term by term, and we have powers, so we can use power rule. Okay, so add 1 to each power. 1/2 plus 1 is 3/2. Remember, we multiply by the reciprocal, 2/3. And yes, we have a C1, but guess what? I'm not going to write it until the end. Okay, so do the antiderivative of x to the negative half. Add 1. If I add 1 to negative half, I get positive half. And then you multiply again by the reciprocal of 1/2, which is 2 over 1. This also has a C2, but again, I am just combining those C's and writing a big constant in the end. Okay? Just do that. Don't do C1, C2. C1 plus C2 gives you another C like that. So this is, guys, this is our f of x. This is called a solution. We have the derivative function. The solution is this, the antiderivative. It's called this is called a family of solutions. With this C, we have a set of solutions, meaning that I can set C equal to 1, C could be 2, C could be 3. So you get like a group of solutions with different C's. But I have this information that allows me to find C. Okay, we have this point on this curve. Plug the point in. Apply f of 1 equal to 5. Again, this means that when x is 1, y is the output is 5. Okay, so plugging that information in gives you an equation with C as unknown. Just put 1 for x. You get 2/3 times 1 to the 3/2 plus 2 times 1 to the 1/2 plus, I don't know what C is, and this output is equal to a y of 5. F is y, so you get 5. Yeah, look at that. This is an equation with C unknown. Solve for C. So here we get 5 equal to 2/3 plus 2 plus C unknown. I don't know how you solve this. I don't know how you like to solve this equation, but you could just move the 2/3 over, do 5 minus 2/3, or you can multiply everything by 3 if you want. You know, it's up to you. Let's just multiply everything by 3. Or let me move the 2 over and then multiply by 3. Subtract 2. You get 3 equal to 2/3 plus C. Okay, now I'm gonna multiply by 3. That should be it, yeah. Multiply by 3. So you get 9 equal to 2 plus 3C. Getting rid of this fraction, move the 2 over, you get 7. And then divide by this 3, you get 7/3 for C. Okay, so we are done. We found the actual function with now knowing C. You can, Joshua. You could solve it. Remember how I said, I don't know, I don't care how you solve these equations, just solve it any way you like. Okay, so here's the final answer. F of x, our function, is equal to 2/3 x to the power of 3/2 plus 2x to the half plus C 7/3. C is 7/3. That's the solution. We found the actual function with C known. Yeah, and you get a bunch of these. You have a bunch of these problems in the book where you have to find C. But again, the book doesn't introduce this notation until later, but you can use the notation if it makes your life simple. All right, guys, that's it for today.